So, good morning, everybody. Let's start. It's 12:07 p.m. I think there are 35 participants till now. Okay, let's start. Am I audible to you? Is my voice is clear to you?
Yes, sir.
Okay. Okay, then last day we have done Taylor series, Maclaurin series, a problem from Taylor series, the convergence of Taylor series. So we already know the if we already know that if a function fz is somewhere analytic, then it can be expanded in a Taylor series. Okay. Now we are going to find the Lorentz series. See Lorentz series here. See, my note is, I think I have shared a note. You are capable to see this. So we are starting Lorentz series from today. So let's start. Let C1 be a circle whose center is at the point Z0 and radius R1. See this diagram. See. Here C1 is the circle whose center is at the point Z0 and whose radius is R1. Okay. Now see the next diagram. Here. Here we consider another circle C2 whose center is also at the point Z0 and radius is R2, but R2 is less than R1. That is, there are two circles. One is C1, that is the bigger circle whose radius is R1 and center is Z0. And another circle is C2, which is the smaller circle whose radius is R2 and also whose center is Z0. Okay. So what we got? We got C1 and C2, two concentric circle with center at Z equal to Z0 and radius R1 and R2 respectively, such that R1 is greater than R2. Now we consider the annular region of C1, C2. What is the annular region of the circle C1, C2? The shaded region in the picture. In this picture, see the shaded region. The shaded region in this picture is called the annular C1 and C2. And we name this T. Okay. So I bigger circles, we take two concentric circles. Concentric circles means two circles whose center is same and the center is z equal to z0. Okay, so the bigger circle is c1 and the smaller circle is c2. Then we considering the shaded region between c1 and c2. This shaded region is called the annular region. Okay, the shaded region in the picture is called the annular region of c1 and c2. That is, we considering the annular region between C1 and C2. Now see here.
So, so I have a doubt that what is this annular region? Means what is the requirement of this annual region? What does it? What is the advantage of
Annular
this? And what?
region, see if you can consider a CD disk. Okay. So the CD disk, the plane of the CD disk is the annular region. Okay. There is a circle. There is a center. Okay. You can visualize like a CD disk. Yes. Or a
Consider, so
bangle, I think. Hmm? Tell
so
me.
why it is called annular region? Means what is the reason? In what
Okay,
respect
this
it is
is the
called?
name. This is the name, annular region. Okay. No, why is there? The region, the shaded region, see the picture. If there are two circles, okay, then the shaded region, this region is called annular region. Just it is called annular region. This is given the name. Got it?
So
Hello?
clear, clear, sir.
It is given the name only. Okay, there is no reason behind annular region. We are taking that region. That region is called annular region. Okay, no other issue is there. Okay. if there are two circles, then the shaded region, like this region is called the annular region. Why circle is called circle? Because circle is named as circle. Therefore, this region is named as annular region. Okay, there is no
Sir,
issue, any other
yes,
issue
I got it.
behind that.
I was
Okay,
just asking the thing that I was asking that the only the definition. I got it properly.
okay,
Yes, I got it clear.
okay. So let's carry on. So now, so there is a annular region D, which is made by two circles C1 and C2. Okay. Now we are considering a function fz, a complex function fz. Now say fz is analytic on the circle C1 and C2. So fz is analytic on the circles, not within the circle. Fz is analytic on the circle C1 and on the circle C2, respectively. Again, fz is analytic in the annular region D between C1 and C2. So there is a function fz. Fz is analytic on C1, fz is analytic on C2, and fz is analytic on the annular region D. Okay, that is in the shaded region. Then at each point in D, fz can be represented as a summation of as a sum of two infinite series. As the sum of two infinite series. The first one is the summation runs from n equal to 0 to infinity an z minus z0 whole to the power n, and the second one is summation n runs from 1 to infinity. Uh, there is a, see there, here, n runs from 1 to infinity bn z minus z0 whole to the power minus n. Okay, now the coefficients an and bn are given by these two things. The first one, an, is given by the integration 1 by 2 pi I integration over c1 fz by z minus z0 whole to the power n plus 1 dz, and bn is given by this integration 1 by 2 pi I integration over c2 fz by z minus z0. This will be z minus z0. Here is a little printing mistake. This will be z minus z0 minus n plus 1 minus n plus 1 to the power minus n plus 1 dz. Okay. So this whole thing is called the Laurent series expansion of the function fz. Okay. So if there is a annular region and a function uh, fz is analytic on the circle C1, C2, and the annular region, then at any point in that annular region, the function can be expanded in the Laurent series. And what is the Laurent series? Laurent series is the summation of two infinite series. Okay, where the coefficients an and bn given by these integrals. Right. So this is the Laurent series expansion of a function fz. Now tell me if anybody has a problem regarding this. If you have any question, you can ask me. So I think there is no question. So I am going to the example. So the example 1, it says that find the Laurent series expansion of 1 by z square into z minus 3 whole square about the point z equal to 3. So we are asked to find the Laurent series of this function z square 1 by z square into z minus 3 whole square about the point z equal to 3. So let me start by fz. We are writing fz in this form, that is 1 by z. We are writing z square like z minus 0 whole square. Okay, no issue with it. We have written fz equal to 1 by z minus 0 whole square into z minus 3 whole square. Therefore, fz is not analytic at the point z equal to 0 and z equal to 3, right? So fz, if I write fz in this form, fz is not analytic at the point z equal to 0 and z equal to 3. So z equal to 3 and z equal to 0 are two singular points of fz. So z equal to 0 and z equal to 3 are two singular points of fz. Now see this picture, see this diagram. Here I have plotted z equal to 0 and z equal to 3 on the complex plane. Then I have drawn a circle whose center is at the point z equal to 3 and the circle is passing through the origin, that is z equal to 0. I am repeating again. I have in this diagram, I have plotted the points z equal to 3 and the point z equal to 0. Okay. Then I have drawn a circle whose center is at the point z equal to 3 and the circle is passing through the origin z equal to 0. Okay. So the radius of the circle will be 3. It is very clear, the radius of the circle will be 3 unit. Okay. Now what I am doing, I am deleting the central point from that circle. I am just deleting the center from that circle. Okay. So when I am deleting the center, the circle without the center is becoming a annular region. Okay. The circle without the center is becoming a annular region, right? So the radius of this annular region, the radius of this circle mod z minus 3 should be greater than 0 because the center is deleted here. So and as z equal to 0, we are not taking the perimeter of the circle, we are considering the inside region of that circle. Okay, so the radius of that circle will be z minus 3 is less than 3. Since we are not taking the perimeter, so it will be less than the radius was 3, so it will be less than 3. Okay, so the annular region will be 0 is less than mod z minus 3 is less than 3. Why it is greater than 0? Because we are deleting the center z equal to 3. So the radius should be greater than 0. And why it is less than 3? Because we are deleting the perimeter also. We are taking the inside region, within the region of this circle. Okay. So this 0 is less than mod z minus 3 is less than 3. This is the annular region. Okay. And in this annular region, the function fz is analytic. Clearly function, the only 2 points the function fz is not analytic is z equal to 3 and z equal to 0. And in this annular region, we are deleting the point, both the singular points. In this annular region is taken such that both the singular points z equal to 3 and z equal to 0 is not considered here. Okay, so in the annular region, 0 is less than mod z minus 3 is less than 3. The function fz is analytic. So the function fz is analytic in the annular region. So we can have a Lorentz series expansion of this function. Okay, now we find the Lorentz series expansion. So we are writing fz as 1 by z square into z minus 3. Okay, then see here, we are writing 1 by z minus 3, we are keeping it as it is. Now 1 by z square, this can be written as 1 by z minus 3 plus 3 whole square. Okay, we are writing this 1 by z square thing by this 1 by z minus 3 plus 3. Okay, so again here in the next step, we have written this form 1 by z minus 3. We have just differentiate z minus 3 plus 3. We have taken a third bracket. Okay. Now here we are writing the 3 in the next step. We are writing 3 z minus 3 plus 3 by as like 3 plus z minus 3. Okay. The only change is there. Okay. We are just writing z minus 3 plus 3 as 3 plus z minus 3. Okay. Now here in the next step, this is crucial. This step is crucial. Here the previous step we get 3 plus z minus 3, okay, in the whole square, in between the whole square. Now our job is to make the leading term unity. Here the leading term is 3, so we are making the leading term infinity by taking 3 common. Okay, since 3 are taken common from a whole square, so it is being 9, it is being, when it is taken outside, so 3 is becoming 3 square, so 9 here, and we get this thing. Okay, now finally this 1 by 1 plus z minus 3 by 3 whole square is written in the inverse form. That is, we are writing this 1 by z minus 3 1 by 1 plus z minus 3 by 3 whole square as 1 plus z minus 3 by 3 to the power minus 2. Okay, so what I have done, we got this thing. We got this 1 plus z minus 3 to the power minus 2. Now, these 1 plus z minus 3 by 3 to the power minus 2, these can be expanded in the binomial theorem. The rule is like this: 1 plus x to the power minus 2. 1 plus x to the power minus 2 can be expanded in the binomial theorem like 1 minus 2x plus 3x square minus 4x cube and so on. By using this rule, we are expanding this to the power, this 1 plus z minus 3 by 3 to the power minus 2 in this step. Okay, this rule, this 1 plus x minus 2, 1 plus x to the power minus 2 has been used to expand this function, this 1 plus z minus 3 by 3 to the power minus 3 function in this step, and we get this expansion. Now after in the next step, we have just make some algebraic manipulations, and finally we get this function fz. Okay, so this is the required Lorentz series expansion. The function in the box is the required Lorentz series expansion of the given function, and this Lorentz series is valid in the annular region. This Lorentz series is valid in the annular region 0 is less than mod z minus 3 is less than 3. Now, okay, is it okay? If you have any question, any doubt about this problem, you can ask me. If anybody has any doubt regarding this problem, you can ask me. Okay, I think nobody has any doubt. It's great. You are doing so much, so well. So why Lorentz series? I am going to the next topic. Why Lorentz series? Why we are reading Lorentz series? The Lorentz series is very much useful to find the poles and residues of a given function. Okay, we already know how to find the poles and residues of a given function, but sometimes there are some critical type of functions, sometimes some functions which looks very critical, and those functions and to find the poles is very difficult. Okay, that becomes method we have already known to find difficult or tough functions which have a very complex form, very complex type, that looks very complex type. Okay, so in that case, the Lorentz series expansion is very useful tool. Okay, if I can expand a function in a Lorentz series, I can find the singularities, the nature of singularities of that function, whether it is a pole or not. If it is a pole, then what is the residue of that function at the pole. Okay, so that is very easy by Lorentz series. So here we are discussing about how to find the pole and residues from Lorentz series. Okay, so let's start it. So if fz has an isolated singular point at z equal to z0, then in the domain 0 is less than z minus z0 is less than R2. Fz has an Lorentz series representation. Okay, see the picture here. Here the bigger circle is C, which has a radius R2. Okay, and the smaller circle is the smaller circle is given by this circle. Okay, suppose this is C1 and the center is Z equal to Z0. Okay, so the annular region, that is the shaded region showed in the picture, is the region 0 is less than Z minus Z0 is less than R2. Actually, we are taking the annular region where only the central point Z equal to Z0 is deleted. Okay, just like the previous example where we have deleted the center point Z equal to 3. Here we have deleted the center point Z equal to 0 and the circle C has radius R2. Okay, so the annular region is going to be 0 is less than mod Z minus Z0 is less than R2. So they says that Fz has an isolated singular point at Z equal to Z0. So Z equal to Z0 is the isolated singular point. We have deleted the singular point, got an annular region, and in this annular region function is analytic because we have deleted the singular point. Okay, so in this annular region the function is analytic. Now Fz is a function, Z equal to Z0 is an isolated singular point of Fz, and in the annular region 0 is less than mod Z minus Z0 is less than R2. The function Fz is analytic. So in this annular region Fz can be written in Lorentz series. Okay, so the Fz can be expanded in Lorentz series expansion. So the expansion is given by this. Okay, so see here the second term of the expansion, this Z minus Z0 has a power minus n. That is, in the next step we can write this as the second term as Bn by Z minus Z0 to the power n. Since this is same, this thing is same, we can write Bn Z minus Z0 to the power minus n as Bn by Z minus Z0 to the power n. Okay, this has been done in this way. Now the main theme is, or the main issue is, this second term, this Bn term, the term containing Bn by Z minus Z0 to the power n is called the principal part of Lorentz series. Okay, where the Z minus Z0 terms in the denominator are the members of principal part of the Lorentz series. Okay, see here, see carefully that here in the an part, in the first part of this expansion, the Z minus Z0 to the power n, that is the Z minus Z0 terms are on the numerator. Okay, but in the principal part, that is in the second part, the Z minus Z0 terms are in the denominator. Okay, and these terms are called the principal part of Lorentz series. The second term, the second series, which runs from n equal to 1 to infinity Bn Z minus Z0 to the power minus n, is called the principal part of Lorentz series. Now I have written the Lorentz series in this Bn by Z minus Z0. If we write it without the summation, then it takes the form this. That is summation n equal to 0 to infinity a n Z minus Z0 to the power n. We have taken the first series as in the summation form. Now we are writing this second series as B1 by for n equal to 1, B1 by Z minus Z0 for n plus for n equal to 2, B2 by Z minus Z0 whole square plus B3 by Z minus Z0 whole cube, and so on. So this B1 by Z minus Z0, this B2 by Z minus Z0 whole square plus B3 by Z minus Z0 whole cube, this part is called the principal part of the Lorentz series. This part where Z minus Z0 terms are in the denominator. I am repeating again, where the Z minus Z0 terms, the Z minus Z0 is in the denominator. Those terms are the member of the principal part of the Lorentz series. where the z minus z0 terms are in the denominator, those terms are the member of the principal part of the Lorentz series. And here also the coefficients an and bn are given by the same integrals. Now, if anybody has any problem up to this, you can question me.
এক্স্যাক্টলি বুঝলাম না তাহলে লরেন্স সিরিজটা কি করে কাজ করছে, তাদের মানে কিসের জন্য মানে ইউজ করা হবে?
হ্যাঁ, সেটা বলছি। Actually, when regarding the number of terms in the principal part, there can be three cases. Okay. So principal part, the principal part may have finite number of terms. So this is case 1. Principal part has finite number of terms. Case 2, principal part has no terms. That is, there is no principal part in the Lorentz series. Okay. And case 3, principal part has infinite number of terms. Okay. Regarding this number of terms in the principal part, there is 3 cases. Okay. I am going to this. Up to this, you have any problem? Okay, I think no problem. So I am again going to this. Now, this is the principal part. This is the principal part of a Lorentz series. Now, regarding the number of terms in the principal part, there may be 3 cases. Regarding the number of terms in the principal part, there may be 3 cases. The case 1 is the number of terms in principal part is finite. Okay, that is, there are finite number of terms in the principal part. The case 2 is the principal part has no terms at all. There is no term in the principal part. Number 3 is the principal part has infinite number of terms. Okay, so there are 3 cases. So let me check the cases one by one. So first is case 1. Case 1 says that if principal part has finite number of terms, and if the principal part has finite number of terms, then z equal to z0 is a pole, and the highest power of z equal to z0 is m. If the highest power of z equal to z0 is m in the principal part, then the order of the pole is m. Okay. So I am repeating again. If the principal part has finite number of terms and the highest power of z equal to z0 is m, then z equal to z0 is a pole of order m. See here. This is the Lorentz series expansion of a function fz, and there is finite number of terms in the principal part. This is the principal part. The terms in the first bracket are the principal part. Okay, so there are m number of terms. Actually, the pole of, now the order of the poles, there are finite number of terms in this principal part. Okay, so z equal to z0 is a pole. Now what is the order of the pole? The order of the pole is the highest power of z minus z0 in the principal part. Now here we say that the highest power of z minus z0 is m. If highest power of z minus z0 is m, then z minus z0 is a pole of order m. Okay. Now what is the residue of fz at the point z0? What is the residue of fz at the point z0? The residue of fz at the point z0 is b1. This b1. The residue of fz at the point z0 is b1. What is b1? b1 is the coefficient of 1 minus z0. See here, b1 is the coefficient of 1 minus z0. Okay, so b1, that is the coefficient of 1 by z minus z0, is the residue of the function fz at the point z equal to z0. I am repeating the whole thing again. If the principal part of the Lorentz series expansion of a function fz has finite number of terms, and if the highest power of z minus z0 is m, then z equal to z0 is called a pole of order m. Then the singularity z equal to z0 is a pole of order m. Okay, and the residue of fz at the point z0 is b1. What is b1? b1 is the coefficient of 1 by z minus z0. So the residue of fz at the point z0 will be the coefficient of the term 1 by z minus z0. Okay. So let's see the example, then it will be clear far more. See the example here. This example. This example says that we are considering the function fz equal to sine hyperbolic z by z to the power 4. Okay. So here for the sine hyperbolic z can be expanded in an infinite series, is an infinite series. The sine hyperbolic z is an infinite series, z plus z cube by factorial 3 plus z to the power 5 by factorial 5 plus z to the power 7 by factorial 7 and so on. Okay. Now here in this point, to solve this type of problems, you have to know the series expansion of different functions. Okay, you can go to the Google, you can go to the go to any advanced book of class 11-12. In the series chapter you can find the infinite series expansion of different functions. So I recommend you to note down the series expansion of some basic functions. The basic functions are sin x, cos x, tan x, cot x, sine hyperbolic x, cos hyperbolic x, e to the power x, e to the power minus x, log 1 plus x, etc. Okay, you can find these expansions in Google. You can Google it, or you can find this expansion in any standard advanced book of joint or কি বলে ওই তো জয়েন্টই বলে অ্যাডভান্স JEE or advanced JEE advanced something. Okay, so now I am writing here the series expansion of sine hyperbolic z is z plus z cube plus z minus z cube by factorial 3 plus z to the power 5 by factorial 5 and so on. Now fz is given by 1 by z to the power 4 into sine z. So 1 by z to the power 4 into the infinite series. So in this next line we get 1 by z to the power 3 plus 1 by factorial 3 1 by z by making by the multiplication. After the multiplication here, we get this step. Here we get the multiplication 1 by z to the power 4 into z, so we get 1 by z cube. 1 by z to the power 4 into z cube by factorial 3, we get 1 by factorial 3 into 1 by z plus 1 by 5 factorial 5z plus 1 by factorial 7z cube and so on. Okay, now my job is to find the principal part. Principal part contains those elements where the term z minus 0 is in the denominator. Okay, so there are only two terms here. There are only two terms where z is in the denominator, and after that all the functions z is on the numerator. So there are only two terms where z is in the numerator. After that all the terms z is in the numerator. So I am writing this in this form. Okay, in the next step, that is, we are in the first bracket we have taken the terms where the z is in the numerator and the principal part is written in the last. The last two term is the principal part. The principal part has the term where the z is in the denominator. So here I have only two terms in the principal part. See, here we have only two terms in the principal part. This is the principal, sorry, This is the principal part, and we have only two terms in the principal part. So since we have two terms, so we have finite number of terms in the principal part. So z equal to 0 is a pole. Now the highest power of z minus 0 is 3 here. The highest power of z minus 0 is 3. So the pole is of order 3. Since there are finite number of terms in the principal part, there are two terms, that is finite number of terms in the principal part. So z equal to 0 is a pole. Now the highest power of z minus 0 in the principal part, the highest power of z minus 0 in the principal part is 3. Therefore z minus 0 is z equal to 0 is a pole of order 3. Now the residue, now what is the residue? See here. Now the residue of z equal to 0 at the point fz is b1. What is b1? b1 is the coefficient of 1 by z minus 0. What is the coefficient of 1 by z minus 0? The coefficient of 1 by z minus 0 is 1 by factorial 3. So the residue of fz at the point b1 is 1 by factorial 3. So this is the case 1. Now if you have a problem, you can ask me. So if you have any problem, you can ask me now. Okay, I think everybody got this. So I am going to the next problem, next case. So case 2. Case 2 says that if principal part has no terms. So that is, if there is no terms in the principal part, then z equal to z0 is called a removable singular point. Okay. So when there is no terms in the principal part, we cannot say z equal to z0 is a pole. Rather, we can say the singular point as a removable singular point. So when there is no term in the principal part, z equal to z0, the singular point z equal to z0 is called the removable singular point, and the residue of the function fz at the point z equal to z0 will be 0. So when there is no terms in the principal part, the singular point z equal to z0 is called a removable singular point, and the residue of the function fz at the point z equal to z0 will be 0. Here we see example again. So here fz is given by 1 minus cos z by z square. So again we know that the cos z can be expanded in an infinite series. An expansion of cos z is 1 minus z square by factorial 2 plus z to the power 4 by factorial 4 minus z to the power 6 by factorial 6, and so on. Now the function is 1 minus cos z by z square. 1 minus cos z by z square. So I am writing it 1 by z square, 1 by z square, 1 by z square, 1 into 1 minus cos z, 1 minus the expansion of cos z. Okay. So here I am writing it after the multiplication by minus 1 here. After the multiplication here. Multiplication by minus 1. So 1 minus 1 plus z squared by factorial 2 minus z to the power 4 by factorial 4, and so on. Now next we are writing, in the next step we have just simplified this. 1 plus 1 and minus 1 cancel out, this plus 1 and minus 1 cancel out, and we get this 1 by z squared into z squared by factorial 2 minus z to the power 4 by factorial 4 minus z to the power 6 by factorial 6. Now the next step is written after multiplication with 1 by z square. So we get 1 by factorial 2 minus 1 by factorial 4 into z square plus 1 by factorial 6 into z to the power 4 plus 1 by factorial 8 will plus into minus 1 by factorial 8 z to the power 6, and so on. So see that here this is the final expansion of fz. in the Lorentz series. And in this series, there is no term where the z is in the denominator. Okay, all the z's are in the numerator. See here, there is no term in the expansion where the z is in the denominator. The terms of the terms of the principal part is looks like the z minus z0 will be in the denominator. That is the 1 by z will be in the z minus 0 will be in the denominator. But here is no term in the denominator. All the z's in the numerator. So there is no term in the principal part. Okay, since there is no term, no z in the denominator, so there is no term in the principal part. So z equal to 0 is a removable singularity, and here in this case the residue of fz at the point z equal to 0 is 0. Now if anybody has any problem, everybody got this? No problem, I think.
सर रिमूवेबल सिंगुलैरिटी का मतलब क्या होता है?
Removable singularity, that is named as removable singularity. Actually this singularity can be removed, okay, by some conditions. Okay, that is the higher case of complex analysis.
Okay.
This type of singularities, if you got this type of singularities where there is no term in the principal part, then for this type of singularities the singularity can be removed by imposing some conditions on the function. Okay,
Okay, sir.
so that is called removable singularity. But this is beyond the scope of our syllabus. Just know about the term removable singularity. Okay, I am going to the case 3 then. Now case 3 says that if the principal part has infinite number of terms, if the principal part has infinite number of terms, then z equal to z0 is called an essential singular point. This z equal to z0 is called a essential singular point. And here also the residue of fz at the point z0 will be b1. That is the coefficient of 1 by 1 minus z0, 1 z minus z0. I am repeating again. If the principal part has infinite number of terms, then z equal to z0 is an essential singular point, is called an essential singular point. And here also the residue of fz at the point z equal to z0 will be the coefficient of 1 by z minus z0, that is b1. Now see the example. Here the function fz is given by e to the power 1 by z. Now we know that the e to the power z can be written in the expansion of e to the power z is 1 plus z square by factorial 2 plus z cube by factorial 3 and so on. Now we want to find the expansion of e to the power 1 by z. What we do? We actually replace z by 1 minus z here. We replace z by 1 by z. Here we replace z by 1 by z in the expansion of e to the power z. The expansion of e to the power z is this. Here if we replace z by 1 by z, we get e to the power 1 by z, and the expansion of e to the power 1 by z becomes the form 1 plus 1 by z plus 1 by factorial 2 1 by z square plus 1 by factorial 3 into 1 by z cube plus so on. Now since the expansion contains the infinite number of terms, we see that this all the terms is in the terms of principal part, and the number of terms are infinite. Here the terms, here this z 1 by z, so z minus 0 is in the denominator. Here z minus 0 in the denominator. Here z minus 0 in the denominator. So this z minus 0 in the denominator, this has infinite number of terms. So the principal part has infinite number of terms here. Okay, so this is the principal part, and in principal part has infinite number of terms. So z equal to 0 is an essential singular point, and the residue of z0 at the point fz is the coefficient of 1 by z minus 0, and the coefficient of 1 by z minus 0 is 1, so the residue of fz at the point z0 is 1. So tell me if you have any doubt. So no doubt at all. Okay. At this point, our complex analysis part has been done. Okay, we are done with the case one. Okay, someone had asked to find the tell the case one more. Okay, once more. So case one, I am repeating case one again. Case 1 says that if principal part has finite number of terms, that is, if there is finite number of terms in the principal part, then z minus z equal to z0 is a pole. Now again we have to find what is the order of the pole. Then to find the order of the pole, we have to find the highest power of z minus z0. That is highest power of 1 by z minus z0. If the highest power of z minus z0 in the principal part is m, then the pole is of order m. Okay, see here. Here, this is the principal part of the Lorentz series. Suppose it has finite number of terms, and the finite number, and there are finite number of terms. Okay, then z equal to z0 is a pole. Okay, now the highest power of z minus z0 is m. The highest power of z minus z0 is m. So z equal to z0 is a pole of order m. Okay, and the residue of fz at the point z equal to z0 will be b1. What is b1? b1 is the coefficient of 1 by z minus z0. The coefficient of 1 by z minus z0 is b1, so b1 is the residue. Okay. Now again we are telling the example. Here sine hyperbolic z by z to the power 4. This is the function. The expansion of sine hyperbolic z is this. We get the function 1 by z squared. So we are multiplying this expansion with 1 by z to the power 4. So we get this. Okay. Now here see that the principal part are those terms where the term z minus z0 is in the denominator. So here the singularity is at the point z equal to 0. So the z minus 0, this type of terms, this number of this type of terms is 2. One is this and one is this. And these two terms are the only members of the principal part. So principal part has two terms. 2 is a finite number, that is principal part has finite number of terms. So z equal to 0 is a pole. Now what is the order of this pole? The highest power of z minus 0 in this principal part is 3. So z equal to z. So z equal to 0 is a pole of order 3. And the residue of fz at z equal to 0 is b1. b1, what is b1? b1 is the coefficient of 1 by z minus 0. The coefficient of 1 by z minus 0 is 1 by factorial 3. So the residue of fz at the point z equal to 0 is 1 by factorial 3. So tell me if you have more problems, we can discuss it. Any doubt can be discussed here. No doubt. Okay, here we have completed the part of this mathematics 2, the complex analysis part of our mathematics 2 syllabus. Okay, from the next day or next week we will start the the series solution of differential equation. Now we are done with the complex functions or complex analysis part. So for today I am completing the class. I am leaving the meeting. The screenshot of this attendance has been taken. Okay, I will give you next. See you next week.
Sir,
Yes.
in the Lorentz series, we are just taking the domain of that series and expanding in the binomial form.
We are just taking the.
That domain of the series and expanding in the binomial form.
Actually, whenever we are for the complex cases, or whenever you are expanding a binomial form, that is whenever you have 1 minus x to the power minus 1, you are expanding it in the binomial series. Then you have a condition. The series will converge when mod x is less than 1. This type of conditions are there. Okay,
Oh,
so these conditions actually comply with our condition of convergence. Okay.
acha. Okay, sir.
Okay, again I am asking any question.